Swayam Prabha. Digital India. Educated India.
That in a closed system, the condition for spontaneity is delta S universe should be greater than 0 for any transformation to take place spontaneously, and if delta S system plus surrounding universe is 0, then that means system is in equilibrium with the surrounding. Point number 1. Point number 2, entropy of all perfectly crystalline substances or solids in their most stable crystalline arrangement is 0 at 0 degree Kelvin. Kelvin's statement of the third law. The total change in entropy of the universe is not a practical criteria for deciding the direction of natural process because it requires very peculiar conditions. System change in entropy at constant volume and internal energy should be greater than 0, or the change in the system entropy at constant pressure and enthalpy should be greater than 0. So these are not practical conditions. Therefore, we came up with a new parameter known as change in Gibbs free energy. So this is the end of last lecture. Now we go on to the statistical origin of entropy. How does entropy come? Clausius gave it very mathematically. Okay. Now can you give a physical sense, some sense where you, me, all of us can understand? A very simple way. So for that we will start with this important diagram, which is variation of entropy with temperature, and this diagram is taken from P.W. Atkins 8th edition. So verbatim, I just took a photo of that and pasted it here, and you can see here starting from 0 degree Kelvin, the molar entropy at very low temperature is very low. We already know that. Molar entropy varies with solid having less entropy compared to liquid. This is liquid, this is solid, and this is gas. This is solid, this is liquid, and this is gas, and this is phase transformation, solid to liquid, liquid to vapor. Molar entropy change accompanying solid to liquid phase transition is solid to liquid is less than the molar entropy accompanying the liquid to gas phase transition. Now I am going to ask you to take this as a question, exam question, and answer. Why is the molar entropy change accompanying solid to liquid is less than liquid to gas? Okay. A gas can occupy a lot more positions in space compared to liquid. That is a simple answer. So this is important for you to remember. So what is this entropy? You are talking about entropy, and entropy is nothing but whatever is the quantity of heat absorbed by the system under some reversible condition divided by temperature. What is the physical meaning of this word entropy? dq reversible by T or q reversible by T doesn't make any sense to me. How do you make sense? Okay. So the statistical origin of entropy is what it attempts by using the language of probability. Okay. So we are going to see, I don't know whether this video will play. I will try to play this. If it doesn't play, doesn't matter, I have something of my own. This I took from MIT. Okay. Source is MIT. I hope it plays. If it doesn't play, doesn't matter. There it seems like it will play.
Have you ever noticed that your room only gets messier over time? Well, guess what? Everything in the universe works the same way. Things only tend to get more disordered on their own. For instance, let's look at this video. Can you tell which side is played forward and which is played backward?
Oh yeah, that's easy. The balloon is exploding.
But did you realize that things got more disordered during the process? The molecules of water went from a nicely organized balloon shape to random droplets flying out in every direction. And how about this one? Which one is played forward?
The right one. Everybody knows that orange juice doesn't assemble itself back into the pulp of an orange.
Alright, how about this last example then? A chemical reaction involving 3 gases, nitrogen, hydrogen, and ammonia.
This one is harder. Are nitrogen and hydrogen going to form ammonia, or is ammonia going to separate into hydrogen and nitrogen?
Well, this one is not so obvious. But there is something that can give us the answer to these 3 situations. The reactions resulted in increased disorder. And in physics, we use the notion of entropy to represent the fact that things tend to get more disordered over time. To put it simply, entropy is a measure of disorder.
But what do we mean exactly by disorder? Let's consider these 3 dice being randomly shaken, and let's look at the sum of the numbers on the dice. For example, if we freeze it right now, the sum is 4 plus 3, 7 plus 5, 12. We will call that the state of the system, and we'll use it to illustrate the notion of order. For example, if the 3 dice all show 1, then the state is 3. Note that there is only one way to obtain this state. All dice must be showing 1. By comparison, there are 3 possibilities to get into state 4. This state has less order than state 3 because the dice could be in any of these combinations and the state would still be 4. Now, there are 6 combinations of the dice that result in the state 5. This state has less order than the previous state because the dice could be in any of these 6 options and the state would still be 5. This example illustrates the notion of disorder. The more possibilities there are for a given state, and the more disordered that state is. Here's a plot that shows the number of combinations as a function of the state. There's a maximum for 10 and 11, which can each be achieved through 27 possible combinations. For example, this shows all the combinations that result in the state 10. This is a state of highest disorder.
Okay, so why is it useful?
Because it tells us how our experiment is more likely to evolve. In fact, as the dice change randomly, they're more likely to produce a 10 or an 11 than a 3 or an 18, because 10 or 11 are much more disordered states. You can see here that the state jumps a lot, but that's because we're only using 3 dice. Now, if you imagine that we have 100 of these dice, starting from the situation where they all show 1s, then this is how the state would evolve. The dice quickly move away from this very ordered state, and over time, the system naturally evolves towards a state of highest disorder.
Now, let's take a second look at the analogy with the tidiness of your room. The ordered state is the state in which every object is in its correct location. For each object that is not at the correct location, the room is more disordered. Just like our dice, there are a lot of configurations in which the room would be as disordered or equally messy. This would be the state of highest disorder, and over time, the room naturally tends to the state of highest disorder. Finally, let's see a practical example where entropy helps us understand the direction of a reaction. If you put some ice into a glass of water and leave it to sit, all the ice will melt. Of course you know this because the water is warmer than the ice. But what exactly is happening at the molecular level? The molecules in an ice cube are tightly packed together into a highly ordered lattice. Molecules inside a solid do move around, but not very much. This is why the ice is cold. Water is a liquid and has a higher entropy. Molecules in the liquid move around a lot more freely, which is what allows liquids to flow. Water molecules bounce off the ice molecules, giving them energy, and the ice begins to melt. Colder water has a much higher entropy than the warm water with ice. Although technically nothing physically prevents all the molecules from spontaneously forming an ice cube, at the molecular level this does not happen because of entropy. Just like our dice, there are many more ways for H2O molecules to arrange themselves in a glass of water than for the same molecules to arrange themselves into an ice cube. This is why heat always flows from a hot body to a colder body.
So now you can appreciate how entropy informs us about the evolution of physical processes. Entropy is a fundamental notion in science because it is a central pillar in thermodynamics, which allows us to understand everything from air conditioners to jet engines.
In fact, entropy helps us to understand the universe at all levels, from a simple system of 3 dice to billions of stars and galaxies. Entropy gives us the direction of the arrow of time. No matter what we're observing, we can be almost certain that the entropy of the universe is increasing.
Okay, that thing was useful. Okay, now do a small problem. Okay, now we will start with a small problem. Instead of the dice they did, this will help you understand a little. So we are going to 2 dice we are going to use instead of 1 dice. Okay, a dice has 6 sides. No? So I am going to roll 2 dice. So what are the total number of outcomes that can come out of rolling 2 dice? What are the possible outcomes? 36 outcomes. And you can write down all the 36 outcomes very easily by 1 on 1 dice, 1 on other dice and so on, you can write 36. So, if you were to roll 2 dice, what is the number that is most likely to come out? That is, you are playing something, right, at home, and you wish to get 6 or you wish to get 12. What is the probability of getting 6? What is the probability of getting 12? What is the likelihood that you will get one number? One number is likely to predominate in this. Likely, most likely. What will be that number? That number will be, you have to look at the total, no? You look at the total, let me directly go to the answer and add here 1 plus 6, 7, 2 plus 1 plus 6, 7, and 3 plus 4, 7, so 2, 4 plus 3, 7, 3, 5 plus 2, 7, 6 plus 1, 7, and the probability of getting 7 will be, the probability of getting 7 will be 7 out of 7 arrangements will give you this. So, when you roll 2 dices, it looks like 7 is most likely to be the outcome every time you do, right? 7 is more likely to be encountered. So, this is what this entropy does. It says that whatever happens, that outcome which has the highest probability to happen is why transformations in nature take place spontaneously. That, so any transformation which has the highest probability of occurrence will take place. This is a simple, very common thing that we all say when we talk about whatever happens around us, right? So, like that, I did this for 1 dice, 2 dices, 3 dices, 4 dices, 5 dices, and calculated all the probability, and you will find that each number of dice, there is one for example 2 dices, probability of getting 6 is 16.667%, with 3 dices probability of getting 10 and 11, which is what you saw in the MIT example, 12.5%, it is the maximum, all other numbers are low in percentage, with 4 dices getting 14 is the highest probable event, and so on, okay. So, you can do for number of dices. So, nature favors that outcome which has the highest probability of occurrence. This is the only thing about entropy. That is what entropy is all about. Okay. Okay. Can you explain this with a little more using chemistry example? We will do that. Let us start with 2 tubes. Okay. And this is what I am going to use this. Now, it has become a tube. Okay. Assume it has become a tube. This is completely covered on all sides. Okay. This is initially vacuum, and this is 2 molecules, A and B. 2 molecules are here. So, this is the initial state. What is the most likely final state? What is the most likely final state? Right? You can draw this in everywhere, and you can have A and B here, and this being empty, same connection. It is open now. So, this one, this is totally empty. B side is, the second side is totally empty. AB on one side, this side is totally empty. I open the wall, still it is empty. There is one possibility. The other second possibility, this is possibility number 1. Possibility number 2 is possibility 2. I am not drawing the whole thing, okay. And the last possibility, there are 4 possibilities. So, which possibility has the highest probability of occurrence? Which probability? There are 4 outcomes. Which has the highest outcome? AB on one side and AB on other side has an outcome of 1 out of 4. This is 1 out of 4 probability. This is where A and B are on both sides equally distributed is. So, If you take a vessel full of gas and connect it to an empty vessel, the gas tends to fill the empty vessel uniformly on both sides because that has the highest probability of occurrence. Okay, nature favors that occurrence, and that is why it is happening. So we use 2 as an example. With Avogadro number you can do, and that can also be a number that you can actually calculate. You find that equal distribution on both sides is a natural phenomena. When I add salt to water, salt getting distributed uniformly throughout the water is a natural phenomena that has the highest probability of occurrence, and that is why it is happening. Very simple logic, okay. So that is the reason why a gas uniformly fills up the space that it occupies. Now, Boltzmann defined this by a term known as entropy of a system is given as K ln W or sigma, where W is the probability of the occurrence of the system. Boltzmann, independently of thermodynamics, came up with this equation. People can come up with the equation, you have to experimentally verify and prove it, right. So Boltzmann came up with this equation. So you know that number of molecules present at constant pressure and temperature is proportional to V, Charles' law, right. So if you were to take n moles of gas molecules occupying V1 liters of vessel and connect it to an empty vessel such that the final volume is V2, then the new positional probability is proportional to whatever is the available volume. V2 is the available volume, therefore new probability is V2, initial probability is V1. So according to Boltzmann's law, change in entropy is K ln V2 by V1. Is it familiar? Somewhere you saw in isothermal expansion, nRT ln V2 by V1, same thing. For one molecule it is K, for Avogadro number of molecule it is nRT ln V2 by, that is a net change in energy, nR ln V2 by V1. So this is what Boltzmann's equation also independently comes up with the same thing that we derived using the second law of thermodynamics. So what about a natural system? A natural system, say nitrogen gas or air is a mixture of molecules. So if you take pure substance, it consists of a number of particles, right? A number of particles which can differ in position as well as energy. Each molecule will have its own position, each molecule will have its own energy. Total energy is the average or sum, average energy of the sum of all energies, and it is usually governed by a distribution. It is not exactly one average, single average, it is a distribution of energy that molecules have. And velocity also is like that. Average velocity of molecule is given by Maxwell-Boltzmann distribution. Every molecule does not have the same velocity, but average velocity is one number. For example, carbon dioxide, we can say for carbon dioxide it is about roughly 400 meters per second, if I remember rightly. I do not remember it correctly. I taught this long time ago, so I am not able to remember. But you know that there is an average energy and there is also a distribution. The total energy of a system is given by the sum of its potential energy, which means electronic energy levels. Potential energy is only by position. Potential energy of a molecule is only by position. So if you take a molecule of nitrogen, its potential energy will be given by how the nitrogen nucleus in one atom is attracted to electron in the other atom, and vice versa. Add up the whole thing, that is the potential energy of nitrogen. Okay. So total energy of the system is given by the sum of its potential energy, which is electronic energy, and kinetic energy. A molecule cannot be quiet except at 0 degree Kelvin, and kinetic energy consists of translational energy, rotational energy, and vibrational energy. Did you study statistical thermodynamics in this lecture earlier? How did you study in first year? It is supposed to be second year portion. Statistical energy is first year, is it? Okay. So total energy of the system is electronic plus translation plus vibration plus rotation, of which electronic energy is potential energy, this is kinetic energy. Increase in the temperature of the system simply increases the overall energy, especially the kinetic energy. Potential energy is not affected much by temperature unless you move the bonds apart so much, otherwise it is not affected. that much. Okay. So, Boltzmann formula is something very important. So, Boltzmann formula of any microstate, entropy of any microstate is given by K ln W, where W is the number of microstates within a microstate or within the state that are present. Okay. So, according to Boltzmann's, we extend this, each microstate, that is a state, consists of number of microstates, and each microstate lasts only for an instant. An instant is very difficult to define, 10 to the power minus 10th of a second, 10 to the power minus 12th of a second, sometimes it can also be 10 to the power minus 16th of a second, femtosecond, like that. It is very, very tiny amount. Constantly systems undergo, every microstate undergoes a change instantly, and so there is a number of distribution of molecules over the available energy levels. And the property of a system is the average of the many microstates that the system can take. So, greater the number of microstates for a given energy, more disorderly is the distribution of energy. Except at 0 degree Kelvin, when the lowest energy level is accessible and there is only one lowest energy state. So, at that state, the entropy becomes 0. So, change in entropy according to Boltzmann formula is given by delta S equal to K ln W2 by W1, where W1 is the initial position, W2 is the final position. You seem to be quite aware of this. Okay. So, now let me take this example, and I am going to go through this very, very slowly. This example again I want to tell you, I just simply worked out the details from the MIT slide. I did not do this, this is not my example, but they gave the answer straight away without working it out. So, I thought work it out. If you work it out, it will be much better for you to understand. So, the details were worked out by me. Example is from the MIT lecture. So, a copper plate of certain dimension 25 degrees centigrade at 25 degrees centigrade is brought in contact with another copper plate of the same dimension at 90 degrees centigrade. So, you have two copper plates, one at 25 degrees centigrade, other at 90 degrees centigrade. Bring them together. So, you have to show that heat spontaneously flows from 90 degrees centigrade to 25 degrees centigrade and not the other way around. How will you go about it? Heat always flows from hot body to cold body and never from cold body to hot body, and that is because of probability. You will see. So, let us take a cross section of the cold plate. Let at any instant of time, one of the atoms possess one quantum of energy, while the others are in 0 reference state energy. So, if the initial energy, number of micro energy states possible for a total of one quantum is 4, since each one of the 4 atoms can possess one quantum of energy at any instant of time, the distribution will be something like this. First atom having one quantum of energy, other 3 atoms having 0, and like that, second atom having 1, others having 0, third atom, fourth atom, S equal to K ln W. So, that is nothing but K ln 4. So, that is the number of states for the initial quantum of energy. Let the hot plate at 90 degree be the surrounding. So, this is system. The cold plate at 25 degrees centigrade is the system, and the hot plate at 90 degrees is the surrounding. Let it possess 5 quantum of energy. 90 degrees, therefore 5 quantum of energy. 25 degree, 1 quantum of energy. So, now let us look at this when we bring together. So, initial entropy of the hot surrounding is K ln W, where W is the number of microstates available for the surrounding. 5 quantum of energy can be shared by 4 atoms in 56 different ways as follows. You will just see this. Okay. So, total is 5 quantum of energy. 5 quantum of energy can be distributed among this in this following manner. So, you can write this. There are so many possibilities you can write out. You will find that the total will be 56. Okay. So, I have just given one example, rest I have written here. 5 quantum of energy in first atom, okay, 0, 0, 0, 0, 0, 0, 5 quantum of energy. Second possibility is 2 in 0 energy state, one atom having 1 quantum, one atom having 4 quantums. You add up the total of energy, everything will be 5. Like that you can write 56 different. There are 56 different ways of distributing 5 quantum of energy among the 4 atoms. You can write such an arrangement and you write the detail. So, when the 4 atoms of hot surroundings at 90 degree with 5 quantum energy is brought into contact with 4 cold atoms at 25 degree with 1 quantum of energy, what is the total energy? 6 quantum. 1 cold atom with 1 quantum of energy is coming together with 4 atoms each, 1 quantum on one side, 5 quantum on other side. When they come together, total energy is 6. Total number of atoms is 4 plus 4, 8. So, how will you find out the number of shared states? When you do that, you will find out that initially delta S system is scale on 4. This is the final answer, 20 different ways you can do, okay. So, final is 20. For the system, change in entropy scale on W2 by W1, W1 is 4, W2 is 20. For the surrounding, initially it had 56 possible states. Now with 6 quantum of energy, number of states is reduced to 20. So, delta S surrounding is scale on 56 by 20 according to Boltzmann formula, not thermodynamic formula, Boltzmann formula. So, delta S universe is scale on 20 by 4 plus scale on 56 by 20, which is nothing but scale on 14, and it is a positive quantity. So, therefore, since delta S universe is positive, energy will flow from the hot body to the cold body. It will not go from the cold body to the hot body because the delta S universe will be negative, minus scale on 14. So, that is why energy does not flow from a cold body to a hot body, and this simple probability. They are simply doing a little bit of probability with numbers and it tells you straight away this is not going to happen. So, that is one way of understanding this, okay. So, you extend the analogy, a molecule has translational energy, rotational energy, vibrational energy and electronic energy. This is potential, these are kinetic. The translation energy is continuous while the others are quantized, okay. So, Avogadro number of molecules, they are present in a very large system. Avogadro number of molecules is a huge system, mathematically huge system, okay. Each one of these molecules at any instant of time can be present in one of the energy states such that the time average energy is constant. So, Avogadro number of atoms 6 into 10 power 23. For each atom, there is a ground electronic state, each atom or each molecule, a ground electronic state, excited states, not one state. For each molecule, translation energy which is continuous, vibration energy, ground state vibrational, excited state vibrational, ground state rotational, excited state rotational energy, ground state vibrational. So, you have everything, it's a total mixture for each and every molecule, and you have Avogadro number of molecules, big system. On an average you have an energy, but you have a big distribution, and that distribution you can, I just took this from the Atkins page number 81, then you find that ground state is highly populated, excited states are populated to different levels by an equation known as Boltzmann distribution, okay. Boltzmann distribution, I don't know whether you remember, N excited by N ground equal to, there is something known as the e to the power minus delta E by kT. This is something that depends on the degeneracy, correct, degeneracy factor. If it is singly degenerate, G equal to 1, multiply degenerate according to that number. So, according to Boltzmann distribution, any molecule will have a population of energy states. Ground state is most populated, excited states are all not zero populated, there is some population, higher the energy, lesser the population. So, this is what is the general equation that you get, Ni, and this I took from Atkins, directly from Atkins. Okay, this is summation is the ground, and this is the for a particular energy state Ei. So, according to the probability, that is outcome of any event, entropy is one where it is the one that represents the maximum outcome of any event. That is the mathematical way of understanding entropy, or a simple way of understanding entropy using layman terms, not thermodynamics, okay. Now, let us take a problem and resolve this. Entropy of mixing of two gases A and B, perfect gases. A and B are perfect gases, that means PV equal to nRT is applicable to them. What is the entropy accompanying expansion of 1 mole of a perfect gas at constant temperature? It is nothing but R ln V2 by V1. We saw this, right, in the second lecture. This is also the result of the application of Boltzmann formula. Both will lead to this formula for 1 mole R ln V2 by V1. Isothermal mixing of two gases A and B. If you mix Na moles of A, mole fraction XA, with Nb moles of B, mole fraction XB, net volume available will be for A and B will be Va plus Vb. Okay. The entropy change for A will be given as XA R ln V2 by V1. The entropy change for B will be given as XB, where XB is the mole fraction. Instead of N, we are using mole fraction. Logarithm of final volume by initial volume. A's initial volume is Va, final volume is Va plus Vb. A and B has been mixed. B's initial volume is Vb, upon mixing it is Va plus Vb. What is the total entropy change? XA R ln Va plus Vb by Va, XB R ln Va plus Vb by Vb, and the delta S mixing is nothing but minus XA ln XA plus XB ln XB. Okay. This is a formula that you already know from earlier studying physical chemistry earlier. Okay. So, the entropy of mixing of gas A and B, perfect gases, is given by mole fraction multiplied by logarithm of mole fraction of the respective components. If it is ABC, it will be XA ln XA, XB ln XB, XC ln XC, and so on. Right. So, this is something that you can, from Boltzmann formula, you can arrive at this formula, which you already know from the other physical chemistry experiments you have done, right. Okay. Now, very simple, I know that you had a lecture of Professor Hemachandra. Okay. No, that is for particles in different spin states. That is a different issue. This we are not looking into anything other than physical hard particles, hard spheres. No such, we are not getting into spin and so on. Okay, just hard spheres. The Boltzmann formula is for such systems. Okay, where so denaturing of protein. Why does a denaturing of a protein take place? Denaturing means there is something about nature that is lost. Okay. I still remember I used to do this experiment when I do enzyme kinetics for in physical chemistry teaching. Papaya, no? You take papaya, remove the peel off the skin, the fruit is there, put it in a mixie, grind it well. After grinding, filter, right? Once you filter, you get some juice. Okay. Add ethanol to the juice, not to drink. Okay. If you add ethanol, then something precipitates out. So, the DNA of papaya, which was present in water, upon adding ethanol, DNA is fully soluble in water. The minute you add ethanol, it denatures, its nature of a double helix is lost. The molecule doesn't know what to do, it precipitates out, showing that I am there, you have found me, guilty as caught. Okay. So, like that, enzymes also or proteins also have structure. All proteins have structure. Okay, some structure, which you know there is some primary structure, which means the sequence of the amino acids. And then you have secondary structure, which tells you now hydrogen bonds present, what links what with what, right? And then you have tertiary structure. That means within the molecule, there are regions which are having some sort of a shape, which is what all our drugs that we use, the principle by which they function is that, taking advantage of that. And there is quaternary structure. Okay. The minute you add some non-solvent, all this structure will be lost and the protein will precipitate saying that I am there, come out of water. Hey, come out, otherwise I will shoot you. All you need to do is add a little bit of ethanol to water. The protein will, if there is any protein, it will fall out as a precipitate. So, nature is solubility, denaturing is insolubility, it is not present. So, denaturing of lysozyme, which is a proteolytic enzyme. Proteolytic means it breaks proteins. So, when we take food, food gets digested. Okay, multiple stages. Here saliva, you have starch amylase that will break down all starch like potato, rice, some small degree. It goes inside, hydrochloric acid is there to break down all proteins to make it into amino acids. So proteolytic enzymes also do the same thing. They break down proteins to amino acids. Body is very careful. Anything and everything you give, you think you are very independent, no? We think, when we think, this is me, I will not do this. Bloody nonsense, okay? Body has its own structure. No matter what you eat, it knows what to take and what not to take. It knows whatever you give, everything will be like a workshop. It will break down. Glucose, go in. Fructose, go in. Galactose, get lost. I don't want you. Mannose, no. Body has a way of, stomach has a way of screening and absorbing only things that it wants. Any protein, any meat, anything that you eat, no meat ever goes inside. Everything is broken down to amino acids. And only amino acid it wants, it will take. All other things, gone. Okay. Any nutrient, it is same thing. Is it required for me? I will take. Not required for me? Go to the waste bin. I don't want you. Okay. In addition to what we do, there are germs in our stomach. Their requirement is completely different. So they may take what you don't want. What your waste is a food for the, maybe food for the germ. And the germ will take it and give you some molecules like vitamins which are useful for you. That is why we never eat for ourselves. We eat for the germs. Because germs, if they are not happy, they will give you stomachache, headache, that problem, this problem. Keep your germs happy and they will keep you happy. Okay. So these proteolytic enzymes are enzymes that break down proteins to constitute amino acids. Lysozyme is a folded protein at 298 Kelvin and it undergoes a conformational transition to a random coil conformation. Random coil means no specific three-dimensional structure. Okay, coil means alpha coil, beta sheets are there. So that transformation takes place at 75.5 degrees. Enzymes always work at some specific temperature because of that. If the structure is lost, enzyme will not work. And when is the structure lost? When there is an increase in temperature. Stomach has to be always maintained at body temperature. Okay, there is a furnace, big furnace heat engine here, constantly generating heat. Okay, if you take an infrared camera and take your body, you will find that this is the belly is the portion where there is a lot of heat coming out because that is where a lot of bond cutting is going on with proteolytic enzymes and other things. Okay, here the heat capacity at 1 atmosphere for the random coil conformation is given as 6.28. The enthalpy change associated with this transition is given. Assuming that the heat capacity of lysozyme does not change much at temperature, calculate the entropy change associated with the conformational transition. Standard problem today you will get in any exam, because this is the application of physical chemistry to biophysical chemistry or protein chemistry. So this problem you should solve or at least look up the solution wherever. In this book I told you I took this from Atkins only. So delta S you have to calculate. So you know that this I have already taught you how to take it from CP folded to CP random through a number of transitions, and you will find that this overall energy delta S is positive. Overall delta S is positive. Therefore, this transformation takes place as written. Okay, and I have another 5 minutes. Maybe I will take 7-8 minutes for the next lecture, and that's it. I am not going to teach you everything. Okay, and this is the summation of what we did in this half. Next lecture, I didn't bring it with me, so I am just going to do it without slides. Okay, so this is my viewpoint. 30 years of teaching, 35 years of teaching, whatever it is. My viewpoint is that this is for to help you. Okay, any form of life, you sit down, whatever you are doing, whatever I am doing, whatever Narendra Modi ji is doing, whatever Amit Shah is doing, what is Stalin ji is doing, what is Kanimozhi ji is doing, anything and anybody, what a parrot is doing, what a crow is doing, what an ant is doing, it is all is a carbon cycle. If you look at it, only thing that goes on is a carbon cycle in this world, nothing else. Whichever way you look, any other chemical transformation is to help this carbon cycle. And what is this carbon cycle? I am going to show you with the picture I have drawn in the next slide. general philosophy that I believe is you either eat or you will be eaten. We have only two choices, not much in the world. Eat well and do work. Otherwise somebody will eat you. Okay. You either direct or you will be directed. People will say, I find you are empty. Can you take this to the bank and deposit? Can you go to Professor Anbarasan and tell him this? Somebody will direct you if you are not directed. Okay. Either you drive like a driver or you will be driven. You will be a passenger. Okay. Driver, passenger, these two, only 1, 0, nothing else. Either you work or somebody will work on you. Okay. So you have to choose something in this, the yes or no. I have one or two. One path you have to choose. Either you synthesize, do something, or somebody will synthesize on you. You will be used as a puzzle and you will be joined by some bonds to connect you to something else and you will become a new molecule, part of a new system. Okay, this is something I believe. And I told you that about the carbon cycle, this I drew on my own. Okay, this mountain picture alone was taken from the internet. Okay, this is to tell you how thermodynamics is so important. So what happens in life is, life cycle is nothing but carbon continuously is going from carbon in the negative oxidation state to positive oxidation state. What is the maximum oxidation state of carbon? +4, carbon dioxide. What is the lowest oxidation state of carbon? -4. So anything and everything you tell me, you, pigeon, everything I can show you the oxidation state in which that person on an average is there. Okay. So this is the carbon in its lowest oxidation state, height of the mountain. Carbon in the highest oxidation state, bottom of the mountain. This goes on continuously. Carbon goes through a number of transformations. Any molecule of carbon will be somewhere in between. Overall life will be somewhere in between. This will be going on in a cycle all the time. Nothing, nobody can stop. That is the universal religion as far as I am concerned. Okay. Whatever happens in the world, the way you picturize that is that carbon is continuously undergoing transformation. That is what we call life. I am able to talk to you, you are able to listen to me. Everything is nothing but carbon cycle. So with that, this is a philosophy I strongly believe in. Okay, based on my experience I believe in. Now let me go to the next part of the lecture. In a few minutes I will just tell you the next part of the lecture, which is about free energy. I get only, it is 5 minutes I have. Okay, so in the 5 minutes, entropy cannot be conserved. Kanna, entropy in உலகத்துல ஏதோ நடந்துட்டே இருக்கு. ஏதோ நடந்துட்டே இருக்கு. ஏதோ நடந்துட்டே இருக்குன்னா என்ன அர்த்தம்? யூனிவர்ஸோட entropy increase ஆயிட்டே இருக்கு. Universe. Entropy, there is more and more disorder being created in the world. To make order in the world, you have to really work hard. You have to expend energy and create order out of disorder. The general tendency of the world is, it will go towards disorder. General tendency is, left to yourself, it will go to disorder. If I am not there, because there is some rule in you, because of respect or out of something you are staying. If I am leaving, next thing you will talk to him. She will go somewhere. She will go somewhere. And this whole thing, disorder is the nature. It is nature. It tends to always go to disorder. Order can be done only by exercising some work. You have to do something constructive, plan, do. Order is not natural to the world. Disorder is more natural to the world. That is the only thing about entropy, nothing else. That's what entropy. Entropy quantifies this disorder. It gives a number. It says there is disorder in the world. Probability, when you speak from the probability point of view, there is disorder. Entropy enables you to calculate this probability. What is the number? Give it some picture. Is this more disordered than this? That number entropy gives. Okay. Disorder is the nature of the world. Order requires effort. You have to put effort to make things in place. And what is the message when it comes to, because oftentimes where in chemistry we study molecules from which we harvest energy. Molecule, there are bonds. The bonds are the source of potential energy. And when a molecule undergoes a transformation like methane gas to carbon dioxide, enormous amount of heat energy comes out. And a small portion will go towards increasing the entropy of the universe. Whichever remaining energy, you have to convert it into positive work. The practical side of thermodynamics is that in any chemical transformation, especially like fuel to energy, how much useful work you can get out of it, how much the universe will take. I give you 100 rupees, I know that you will take minimum 30 rupees, only 70 rupees you will put in my bank account. That 70 rupees in the bank account, I don't know where, bank clerk knows my password, Aadhaar card, everything. I don't know how much bank clerk is going to take. In my account, effectively 50 rupees will be there, manager will take 10 rupees. So you are the messenger, you took 30 rupees, clerk took 10 rupees, manager took 10 rupees. In my account, when I see message that comes in my mobile, 50 rupees deposited, I gave you 100 rupees and you will say, I deposited 70 rupees. So what we are trying to figure out is, where is this entropy going? Why is it 50 rupees? Why 100? What happened to the 100 rupees is what the practical side of thermodynamics to chemistry. Okay, philosophy is what we use as a tool to find out that this is not possible. You cannot convert all the energy in a bond to useful work, because universe, whenever any transformation of this kind takes place, universe says, where is my commission? Give me my commission, otherwise I will not allow. I am using local terminology, I am not using scientific terminology, but the point I hope is conveyed very clearly that this is what happens. Whenever any natural transformation takes place, in order for that to be spontaneous, universe will take away entropy. It will take some of the heat energy and increase its disorder. For us, that is what is important. I thought all my 55.5 megajoules of energy from 1 kilogram of methane will be available. Why is it that only 30 megajoules I have got? So you know the rest. Rest on to increase the entropy of the universe, it went to increase the entropy of the tire's outer surface, and so on. It goes on to many other factors. So this is the important lesson. Okay. I had one more problem. I don't know, maybe delta G, if I can do that. I may left the paper. So how will I, if you are interested in the notes, so for lecture 1, lecture 2, how will I send it to you? As a PDF file I can send. Huh? I can send it as a PDF file. So in case you want to slowly go through it at your own leisure, how will I do it? Yeah, I will share with one of the student, but you have to give me email. So I will share PDF file, which you can circulate among yourself. And during exam, don't study all of it. Caution, do not study thermodynamics book before exam, unless you want to go to mental hospital. Okay. Do not do it for any subject, quantum mechanics also for that matter, organic chemistry also, inorganic chemistry also. At your level, what are the key issues? What are the key points? Study the key points. Summarize in the form of few page sheets, study then go to exam. From exam point of view, that is enough. With experience, everything you are going to learn. Okay. You are going to experience a lot in life. Then you will say, this is applicable, this is relevant. Okay. Very few of us can actually absorb what is given in a textbook. Textbook is just meant when you don't get sleep, open the textbook, you will get sleep. Okay, depending on your subject, some people get sleep with organic chemistry, some people get sleep with physical chemistry, some with quantum, some with inorganic chemistry. So when you have sleep deficiency, study it. Otherwise, focus on the key issues at the level which is of relevance to you, practical value to you. Do not study. My strong thing is, unless you are mad, do not study textbooks. Not necessary. Okay, textbooks are too much of packed information. Even one chapter will take, to understand it thoroughly, one chapter will take a lot of time. Okay, so that's not necessary. Okay, so I think I will send the third lecture notes to you as a PDF file, so I don't have to teach. So you go through it, where what we are trying to do is study how an equilibrium, for example, any chemical thing, no, any physical thing is an equilibrium. Did you know that dissolution of a salt is an equilibrium? Do you know that NaCl, solid plus water? Did you know that this is an equilibrium? Did you know that this is an equilibrium? Dissolution of a salt is in equilibrium. Vaporization of a liquid is in equilibrium. All these things can be studied by variation of G with P, variation of G with T. Variation of G with P P is the partial pressure. Variation of free energy, standard state free energy, is a partial pressure. This is a standard one equation, that is more than enough. This equation automatically, when you apply to the equilibrium ammonia, it will become an equilibrium constant. This is an equilibrium constant. Why is it an equilibrium? So suppose I write, as you saw in the MIT lecture, 3 and so this is gas. So for each term you apply this. You know that concentration of ammonia, the whole squared, divided by concentration of nitrogen into concentration of hydrogen cube is known as, normally what is it known as? Reaction quotient Q. Reaction quotient. It is equilibrium constant only when delta G equal to 0. Okay, reaction quotient can be obtained by using the term for each one of these. Ammonia, you can use a G expression. You can use the expression for nitrogen, and what you will find is at equilibrium, delta G, you can show this, delta G naught minus RT ln Kr Q by K, at equilibrium it will become K. Q, I don't remember this minus or plus, delta G equal to delta G naught plus RT ln Q, I think. I don't remember this, but you can, from this equation you can derive, and for every include solubility is in equilibrium, vaporization is in equilibrium, solid to liquid is in equilibrium. Okay, everything is in equilibrium. In this case, the equilibrium constant is known as solubility. Solubility is known as the equilibrium. So this was the part I wanted to take next time. Apply this to chemistry, but I don't have time. If I am given time, I will come back to you. Okay, Thursday 1 more hour. That means I will teach on variation of free energy with pressure and temperature. Okay, that's it.
SwayamPrabha, Digital India, Educated India.